Hello, AP Chem. I'm going to give another installment of notes for Chapter 12. Chapter 12, 1, 2, and 3 have already been recorded and on the YouTube channel. They basically started us out as defining what we mean by a rate law, or defining the rate actually first, and then we talked about the rate law. Rate equals K times the concentration of the reactants raised to the power that is called its order. We learned that one way to determine the value for K and the value for the orders of each reactant is by the initial rate method. There's another way to do it. It's called the graphical method or the graphical approach, where you graph the concentration of one of the reactants or products as a function of time. The curves or lines that you get when you graph those will have different characteristics depending on the order of the reactant, and by identifying which of the graphs gives a straight line, you can then also use the slope of that straight line to determine K. So let me talk about that for a little bit here. We're going to call it the integrated rate law. The rate law that we learned previously, rate equals K, A to the M and B to the N, is called the differential rate law. Those are calculus terms because of the way they are derived mathematically. You don't have to necessarily know the calculus, just know that the rate law is called the differential rate law when it's in the form of the one we have at the start here. Let's say we have a single reactant A, and that A turns into products. Well, remember, the rate is defined to be -1 over A times the change in the concentration of A over time elapsed, and that rate can be found to fit into a formula that would be a rate constant K times the concentration of A raised to N. So K is going to be small or large depending on whether the reaction is slow or fast, and N is going to be the order with respect to A, and depending on what N is, K will have different units. We talked about the units for K previously. Okay, so let's develop some integrated rate laws for first order reactions, so where N equals 1, second order reactions where N equals 2, and then 0th order reactions where N would equal 0. So we happen to know that there's a reaction, 2N2O5 yields 4NO2 plus O2, where the rate is first order. So the rate is defined as -1/2 the change in concentration of N2O5 over the change in time, and it's equal to K times the molarity, moles per liter of N2O5. For this first order reaction, you could graph the concentration as a function of time, and you could graph the reciprocal of concentration versus time, and you could graph the natural log of the concentration of N2O5 versus time. Now, why we do that? Well, it has to do with the possible calculus derivations that you could get for the different orders. We find that because we see the three graphs here, we find that because it is first order, that the concentration of N2O5 as it goes down means the reaction rate goes down. So the concentration of N2O5 versus time in the left graph shows that it's a curve. It's not linear, it's a curve. However, if you instead plot the natural log of concentration of N2O5 versus time, you actually get a straight line. And when the natural log of the concentration of the reactant versus time is a straight line, it actually proves that it is a first order reaction. So identifying the straight line. When the natural log of N2O5 versus time is your straight line, that means when you graph it by the graphical approach that you've identified that it's first order. Just for kicks, we'll show that the 1 over the concentration of N2O5, the reciprocal versus time is actually a positive slope because the less you have, the higher the reciprocal is, and that it is not a straight line. It's easily identified to be a curve. So when you make these three graphs for any particular experiment, one of the three will be a straight line and the other two will be a curve. So depending on which one's a straight line, it tells you what the order of the reaction is. In this particular first example I'm showing you, natural log of concentration is our straight line, so that tells us we have a first order reaction. Now, looking at that straight line, we could use what we know about straight lines from math to create a formula that would allow us to calculate the concentration of N2O5 at some particular time in the future based on the original concentration of N2O5. So looking at it, the graph that's linear, the middle graph, the natural log of N2O5 is y and time is x. A linear graph is going to mean that y equals mx plus b. So if we substitute for y with natural log of N2O5, we substitute for b with the natural log of N2O5 at the beginning. So in other words, the natural log of the original N2O5. So I've identified it in the equation as N2O5 0 for 0 time. So at the beginning of the reaction, you have some initial concentration of N2O5. So that would be, the natural log of that would be b, the y-intercept. Then the x would be t, y equals mx plus b. And it turns out that m, the slope, which is negative, is actually negative k. So, and this comes from the derivation using the calculus. So that means that we have taken this linear graph and we've created from this linear graph a useful formula that could be used to calculate the concentration of N2O5 at any particular time in the future, just knowing the K value and knowing the concentration of N2O5 originally. So you can work it either way. If you know the reaction is first order, you can use this formula, natural log of N2O5 equals negative KT plus ln of N2O5 at time 0, to find anything you want to find in the formula based on knowing the other numbers. Or you can use the fact that this formula works for first order to identify when you use the graphical approach on an experiment that you have a first order reaction. So if you get this linear graph for natural log, you know you have a first order reaction. And if you get the graph, if you make the graph, you can find K. Or if you happen to be given K in some problem and you know that from the problem that you have a first order reaction, you could calculate the concentration of N2O5 at some time that you plug in for T. Okay, so that would be the approach that you would take if you're doing the graphical approach, or if you're just using an integrated rate law to solve a problem. Okay, for a second order reaction, rate equals Ka squared, we find that the integrated rate law is going to take the form of 1 over the concentration equals Kt plus 1 over the original concentration. So that means that our straight line will not be the concentration or the natural log of concentration. The straight line will be the reciprocal of the concentration versus time. So if you find when you graph your data that the reciprocal is the straight line, that tells you you have a second order reaction. So based on that, using some similar analysis from previously, we find that 1 over the concentration versus time is linear, so it fits the format of y equals mx plus b. So y being the y-axis, 1 over concentration, equals k. Now this time it's not negative k, it's positive k because the slope is positive and k is positive. T, your x value, plus your y-intercept is going to be the reciprocal of the concentration at time 0. Now, for these reactions, the half-life is found to be 1 over K times the concentration of A naught. That would be the equation for the half-life. Now, I think I forgot previously on the previous slide, let's go back to that mathematically you can plug in numbers and solve for the fact that the half-life of a first-order reaction is that the half-life equals 0.693 divided by K. So 0.693 is actually the natural log of 2, and that's why it's a constant 0.693. So by using your formula, you could derive this. It's kind of fun to do, but you could derive what would be T if N2O5 is half of N2O5 at time 0. That'd be called the half-life. Now notice the half-life for first order does not depend on concentration. Doesn't matter what you start with, it'll still be the same amount of time to go to half. So if you know anything about nuclear reactions or nuclear decay is always first order. It always has a half-life that is a constant. You always have like a 500-year half-life for an isotope, and it doesn't matter how much of the isotope you have, it'll always be 500 years before you have half as much of the isotope left. So half-life is something else we can get when we have this integrated rate law. Half-life meaning how long will it take before you only have half of your original amount of reactant. So for first order, half-life is 0.693 over K, and for second order, half-life is 1 over K concentration of A at time 0. So half-life for second order does depend on which or what original concentration you have, unlike first order where it doesn't depend on concentration. Half-life for second order does depend on concentration. Okay, I apologize. It's a lot of math here, but if you know your 3 different orders and the integrated rate law for them and the half-life equations for them, it actually comes in quite handy in analyzing kinetics. Okay, so if you find that the reciprocal concentration graph is your linear one, then you know that you have a second order reaction. And from that graph, you can use the slope to find K. And then you can also use the integrated second order rate law to solve problems that have to do with you start with this much, the K value is this, the time is this, how much do you have left at that time? All right, now similarly to what we just did for first and second order, let's go back and let's fill in the gaps with zero order. Now for a zero order reaction, concentration of A is to the 0 power, so that's just 1. Anything at 0 power is 1, so rate equals K. In other words, you have a constant rate. The rate does not depend on the concentration of your reactant. The rate is constant. So in that case, your linear graph is actually going to be the one with the concentration of A versus time. The concentration of A versus time is going to be that the concentration of A goes down at a constant rate. So you have a constant slope, so you have a straight line. Using the analysis of trying to create a y equals mx plus b out of that, you would get concentration of A equals negative KT plus A naught, where K is your rate constant, or in this case, K is your rate. K is simply the rate of the reaction because it doesn't depend on the concentration. So rate equals K and A equals negative KT plus A at time 0. Now using some substitutions, like maybe you plug in 2A naught for, or half A naught for A, you can get that the half-life is actually A at time 0 over 2K. So first order reactions often occur in like situations where you have catalysts like metals, and those metals are catalysts for gaseous reactions, or if you have enzymes in some biochemical reactions. You can end up with first order reactions occurring. I'm sorry, do I mean to say zero order reactions? Let me check the book real quick. I think I might actually mean, because I'm including it here on this slide. Sorry about that. should have got my ducks in a row here a little better. But I think I meant to say that zero order reactions often occur when you have, so I'm using the textbook like you should be using the textbook. Yes, zero order reactions often occur on surfaces of catalysts like metals or gaseous reactions, or enzymes like some biochemical reactions. So sorry about the misprint there. Cross out first, put in zero order reactions. So graphing your data versus time is a standard way to find the order of the reaction and also the value for K. So you can get both the K and the order. So we've got two approaches now for finding K and for finding the order of the reactant. We've got the initial rates method, and then if you have only one reactant, you can use the graphical approach to graph the concentration versus time and the natural log of the concentration versus time and 1 over the concentration versus time and see which one is linear. And then you can get the K value and the order. Now, this only works if you have one reactant that affects the rate. If you have two reactants that are both affecting the rate, then it gets more complicated, obviously. You have one reactant, it's changing concentration and it's affecting the rate, and then you have a second reactant and it's changing concentration and it's affecting the rate. You can't use a graphical approach in that case. So how could we use kind of this integrated rate law approach if we did have more than one reactant? Well, I just told you couldn't, except there's a sneaky way to do it. So let me tell you about the sneaky way to do it. You can actually use the graphing approach to determine a rate law if you have A and B both affecting the rate of the reaction, or you can even have A, B, and C affecting the rate of the reaction. So in order to do that, it's necessary that one of the reactants' concentration is constant. Now you're thinking, well, you can't have a reactant have a constant concentration because it's going to be losing its concentration as it's used up. But you can kind of fake it. You make one of the reactants' concentrations very large, say 100 times more than another chemical's concentration. So maybe one of them has a 10 molar and the other is 0.1 molar. So A might be 10 molar and B might be 0.1 molar. Now, because A is so much larger than B, A basically doesn't change. A little bit of it gets used up, but if you use up 0.1 molar of 100 molar, that's 99.9 molar still left, which means you basically haven't really put a dent in the amount of A, even though your B may be all used up by now. So by making one concentration of one reactant much larger than the other reactant, you can effectively turn a reaction which has two reactants both affecting the rate into a reaction where only one reactant affects the rate. So the low concentration reactant is going to affect the rate. The high concentration reactant, because it's constant effectively, it's negligibly changes, it's going to be not affecting the rate. So let me show you mathematically how that works. Let's say we had two concentrations, A and B, and they both affect the rate. We would have rate equals K, A to the M, B to the N. But now let's make A much, much larger than B in concentration. If A is much, much larger than B, then basically the rate constant times A to the M is not, that part of the equation is not going to be changing as the reaction occurs. So I can basically consider K, which is already a constant, and A to the M, which is going to be effectively a constant because it's not going to be changing because it's so large. I can basically bundle them together and call it K prime. And now by substitution, my rate law looks like rate equals K prime B to the N. So now I've effectively turned a rate law with two reactants into a rate law with only one reactant affecting the rate. And so now by graphing the concentration of B versus time and the natural log and the reciprocal of it, I can use the graphical method to solve for N and K prime. Now K prime is not K, but K prime is a constant. Now, let's say, obviously, in that case, you'd probably want to know what M is as well and what K is. This only gives us the value for N and the value for K prime. So how do we get back to the original equation, rate equals K, A to the M, B to the N, and figure out what those other two numbers, K and M, the order for A, are actually equal to? Well, obviously, one way to do it would be just turn the reaction around and make B much larger than A. Right? You could do that, and then by a similar way, you could figure out what M is. But usually, I think what most people do is they simply keep A much larger than B, but change it by some factor. So maybe you cut it in half or you double it. Well, it's still much larger than B. But if you have that equation, K prime is equal to K A to the M, and if you double A and K prime doubles, you know M is going to be first order, because K prime equals K A to the M. And if you double A to the first power, that means K prime doubles. If you double the concentration of A and run the reaction again, plot it, and you get another K prime, and let's say K prime multiplies by 4, it quadruples. Well, you only doubled A, but K prime quadrupled. That must mean A is to the second power. If changing A by a factor of 2 doesn't change K prime, that means A is 0 order. In other words, A to the 0 power, in other words, K equals K prime. So by doing that, you can figure out that M, and you know the A, so K prime can be used to calculate the actual true value of K. So that's usually the approach we use, is we simply run the reaction twice, one where A is much bigger than B, and then another where A is much bigger than B, but different by a factor of 2 from the previous reaction. And then look at how changing A, doubling it or cutting it in half or whatever you did, affects K prime. And then by doing a little math, you can figure out. So by that time, you've got N, you've got M, and you've got K. So because this is all kind of sneaky math here, this approach is known as the pseudo rate law approach, or the false or sneaky rate law approach. Okay, so that gets us up to 12.4, where we've gotten through the integrated rate law. And there is actually a really good summary of everything 12.1 through 12.4 in the book on pages 488 and 489. It's a little purple box called Let's Review. And reading over that, making sure it all makes sense would be great to do before you move on to the second half of the chapter, 12.5, 6, and 7, where we're going to talk about mechanisms, and we're going to talk about a chemical model for kinetics, and we're going to talk about catalysts also in 12.7. Okay, well, thank you for your attention on this. Sorry I droned on and on about it, but I wanted to kind of explain the math behind it. And let's make sure in class that you ask the right questions to get your mind wrapped around the math for this, because the math is kind of maybe a little trickier than math we've used up till now. So persevere, ask questions, and let's figure out the math for this, for these two kinds of rate laws, these differential rate laws and these integrated rate laws, and the two approaches for finding K and for finding orders, which are the initial rates method we talked about in the previous video, and then this one, the graphical approach. Also, the homework will give you some practice in plugging in values for K and T and concentration into these three integrated rate laws and solving for the concentration at different times. Okay, thank you for your attention.